Looking at homework from section 6.4. This is question number 5. The number of hours of reserve capacity of 10 randomly selected automotive batteries is shown to the right. Assume the sample is taken from a normally distributed population. Construct 80% confidence intervals for A, the population variance sigma squared, and B, the population standard deviation sigma. So we have 10 values that are decimal values. And for us to do this process, we're really going to turn to technology to help us speed it along. We could do the process that we learned back in section 2.4 on how to find the mean, variance, and standard deviation to build a table, but the TI-8384 graphing calculator is going to make it a lot easier. So what we're going to do first is we're going to press the Stat button on our calculator. That's going to take us to the Stat screen. You'll notice that Edit is highlighted as your tab, and Edit is the first menu choice that is highlighted. If you go ahead and press Enter, that's going to take you to the Stat List Edit screen. And what we're going to do here is we're going to enter these 10 values in L1. So if you have values in L1 already, you need to clear those out before you begin this process. And so when you're all finished entering those values, it should look like this. Once we've got the values all entered, then we hit Second and the Mode button, and that will take us back to our home screen. Now your home screen may not be blank. I just put a blank screen here. If you've done other calculations, you'll see the other calculations you've done, and that's fine. It's not going to interfere. And then we need to go back to the Stat menu. So we hit the Stat button, and that takes us back to that Stat screen. This time we're going to move the tab at the top from highlighting Edit to highlighting Calc, and the way we do that is by pressing the right arrow button. Once the Calc menu is highlighted, you'll see several new menu options, and the very first one says One Variable Stats. That's the one we want, so we're going to go ahead and press Enter, and when we press Enter, that's going to put the One Variable Stats command on our home screen. Pressing Enter again will give us all the statistical values that we need. Now the only thing that we actually need from this is the standard deviation, and we're looking at the sample standard deviation, which is the SX value, the 0.2235297,644 value. All the other things are not important for us in this particular problem. So the only thing we need is the sample standard deviation. We'll keep that. We're not going to round it at this point. We don't round values until the very end, so we want to use as much of the value to be as precise as possible. Once we've got that value, then we can find the chi-square values. If you want to look at a graph of a chi-square distribution, that can help you kind of determine what it is you're looking for. So remember, the chi-square distribution is a non-symmetric distribution. We have these two values, chi-square L and chi-square R, and in those two tails, even though it's not symmetric, we're putting those values in such a place that the two tails will have the same amount of area, and that the centralized area is our level of confidence. So in this example, we're doing an 80% level of confidence. So in that central region, we have 0.8, or I put 0.8000 as our area. That means there's a total of 0.2000 area in the two tails. When we split that in equal portions, each one of those tails has 0.1000 as its area. When you use the chi-square distribution, it's unlike the standard normal distribution because the chi-square distribution requires you to figure out how much area there is to the right of a given value. So let's look at chi-square L. How much area is to the right of chi-square L? Well, that would be the area 0.8000 and the right-hand tail of 0.1000. So that's a total of 0.9000. We do the same thing for the chi-square R value. We want to determine how much area is to the right of that. So to the right of that is just the right-hand tail, which is 0.1000. These two areas, the total area to the right of chi-square L and the total area to the right of chi-square R, will always add up to 1. So you can always do a little quick check to see if they do. So let's go ahead and keep this picture as a reference. And now we can figure out the areas to the right. The area to the right of chi-square L is 0.9000. Area to the right of chi-square R is 0.1000. And then we also need our degrees of freedom. The degrees of freedom, one less than the sample size. We had 10 values here, so the degrees of freedom is 9. Once we've got those values, we can turn to the chi-squared distribution table. So our degrees of freedom, remember, are 9. Area to the right of chi-square L is 0.9000. The area to the right of chi-square R is 0.1000. This is our chi-square distribution table, at least part of it, the only part that we need for this problem. So how do we figure out chi-square L, the actual value on the axis? Not the area, but the value that makes that area happen. Well, we combine our degrees of freedom with the area to the right of chi-square L. So the degrees of freedom were 9, and the area to the right was 0.9000. On our table, it's 0.90 at the top. So we find 9 degrees of freedom along the left, and the 0.90 at the top, and where those two meet is at 4.168. That's the value of chi-square L. For chi-square R, we do something similar, but with the area to the right of chi-square R, which is 0.1000. On our table, it's 0.10. So we find where the degrees of freedom 9 intersect with the 0.10, and that's at 14.684. So now we have the value for the chi-squareds. What are we going to do with those values? Well, we're going to enter them into our formula that gives us the variance and standard deviation. So how do we do that? This is our formula for the confidence interval for the variance. Notice sigma squared is in the middle. It's n minus 1 s squared over chi squared r, and then n minus 1 s squared over chi square L. So, a few things you want to realize about this particular formula. N minus 1 is your degrees of freedom. The s is the standard deviation, but you have to square it, so it's actually the sample variance that's in the numerator here. And then for the chi-square values, the chi-square L value is on the right, and the chi-square R value is on the left. The reason for that is that the chi-square R value is going to be a larger number, and when you have the larger number on the bottom of the fraction, that makes the value of the entire fraction smaller. Making the bottom of a fraction bigger makes the value of the fraction smaller. So that ensures that the fraction on the left is smaller than the fraction on the right. So what we're going to do is we're going to insert all these values and see what happens. So we get 9 times the 0.2235297,644 squared. That's in both numerators. The left-hand denominator will have a 14.684. The right-hand denominator will have a 4.168. When we evaluate these on our calculators, we get 0.0306244,893. 0.1078910749 on the right. This is our confidence interval for the variance. So we're going to round this to 3 places now. And so we're looking at 0.031 to 0.108 for our confidence interval for the population variance. We also needed to interpret those results. So we had an 80% level of confidence. When we're finding a confidence interval, that's how confident we are that the actual population value for, in this case, the variance, falls within that interval. So with 80% confidence, it can be said that the population variance is between 0.031 and 0.108. That would be choice A. We're always expressing how confident we are that the actual population value is between the bounds of our interval. Not less than that, not more than that. So that's the variance. What about the standard deviation? Wow, that's been a lot of work so far, but we luck out because everything that we've done so far can be applied to the standard deviation. We don't have to recreate that work. So the confidence interval for the population standard deviation is, well, we just got all that stuff done for the variance. what we're going to have to do now is take the square root, because remember that the standard deviation is always the square root of the variance. So if you take that inequality statement that we had for the variance and take the square root of each part, we'll get our answer for the standard deviation. So we'll start with our variance inequality. We take the square root of everything. When we take the square root of the sigma squared in the middle, it just becomes sigma. And then the square roots of those values give us 0.174998547 is less than sigma, which is less than 0.32846777684. Rounded to 3 decimal places, we get 0.175 to 0.328. And that's our confidence interval for the population standard deviation. Just like we saw when we went through standard deviation and variance way back in chapter 2, all the work is really rolled up in finding the variance. Finding the standard deviation is easy once you know the variance. You're just taking square roots. So let's interpret this result. Again, when we find a confidence interval, the level of confidence tells us how certain we are that the population value falls within the bounds of our interval. So which choice would that be? Well, we're an 80% level of confidence, so choices C and D are out because those say 20%. Choice A is about being less than a value. Choice B is about being between two values. So our choice here is choice B, because with 80% confidence, we can say that the population standard deviation is between 0.175 hours and 0.328 hours. Now, always check your answer. How do we check our answer? Well, when we found the standard deviation on the calculator, it was 0.22 something. That number needs to fall between these two bounds, 0.175 and 0.328. It won't be exactly in the middle, but it needs to be between those. If it's not between those values, then you've done something wrong. So you need to go back and find where your error is. But this time we did it right. This is 0.175 to 0.328, choice B, and that's your answer.